안녕하세요, 올바름입니다. 오늘은 조금 긴 내용이에요. 아마 이 시청 시간 보이시죠? 엄청 깁니다. 근데 시간을 내서 여러분들과 함께 보고 싶었던 내용이기도 하고, 그리고 저도 오랜만에 보는 내용이기도 합니다. 이게 굉장히 긴 영상이고 썸네일에 제가 알림을 해두긴 했는데 그래도 보시겠다고 오셨으니까 어서 오세요. 반갑습니다. 자율주행을 구성하는 3요소에 대해서 모빌아이의 회장이자 CTO, 최고 기술 책임자를 CTO라 그러는데 암논 샤슈아의 강의입니다. 뭐 최근 거는 아니고 최근 것도 제가 나중에 계속해서 업데이트를 할 건데요. 2016년 6월의 자료입니다. 그런데 잘 정리가 되어 있어서 가져와 봤고요. 자율주행에 대해서 일단 클릭을 하셨기 때문에 관심이 많으시다고 가정을 제가 하겠습니다. 그래서 단순히 주주로서 접근하기보다는 저는 이제 이쪽은 그냥 재밌어서 공부한다는 생각으로 접근을 해보고 있습니다. 뭐 일단 객관적으로 주주로서 그런 확증 편향으로서 벗어나기 위해서 공부한다는 생각으로 어떤 얘기를 하는지 알아봐야겠죠. 모빌아이는 거의 모든 면에서 중복성을 통해서 자율주행의 안전성을 많이 높이려고 하고 있는 기업입니다. 오죽하면은 센서도 두 스택으로 나눠서, 두 개로 나눠서 하나는 11개의 온리 카메라로 이루어진 첫 번째 시스템이랑 라이다랑 레이더로 이루어진 두 번째 시스템으로 구성이 되어 있습니다. 그래도 여전히 카메라 중심적입니다. 실시간으로 소통하고 인식하고 하는 거는 카메라가 우선적으로 사용되기 때문입니다. 다양한 접근법에 있어서 모빌아이에 대해서 이해하는 시간을 가져보면서 샤슈아 교수님의 강연을 듣는 계기로서 좋은 시간을 가졌다고 생각됩니다. 우선은 짚고 넘어갈 점은 이렇게 간단하게 세 가지를 짚고 넘어가 보죠. 중요한 것 중에 하나입니다. 목차 같은 그런 개념이에요. 센싱은 센서를 통해서 정보를 취득하는 일입니다. 여기에 이렇게 나올 겁니다. 차가 주행하는 데 있어서 정보를 얻는 파트예요. 두 번째는 맵 데이터를 활용하는 방법입니다. 맵 데이터는 이제 아예 사용하지 않을 수는 없어요. 얼마나 더 사용하느냐의 문제겠죠. 뭐 얼마나 강화돼서 사용하느냐, 얼마나 계략적으로 사용하느냐, 이렇게 해도 객관적으로 볼 수 있을 것 같습니다. 웨이모처럼 풀로 3D로 포인트 클라우드를 다 돌려서 이렇게 맵을 만드는 경우도 있고, 모빌아이처럼 랜드마크와 의미적인 데이터들만 사용하는 경우가 있습니다. 그런데 모빌아이의 경우를 보면 굉장히 고민을 많이 했다, 이런 생각이 들긴 합니다. 그리고 다중성 문제라고 하면은 조금 애매할 것 같은데 이 드라이빙 폴리시 문제입니다. 한마디로 도로상에는 멀티 에이전트 게임이라고 표현을 했는데 굉장히 다양한 객체들이 있죠. 차량도 있고, 그러니까 내 차도 있고 상대방 차도 있고, 그리고 보행자도 있고, 굉장히 다양합니다. 그런데 자율주행차가 사람들이 많은 도로를 지나는데 컴퓨터처럼 행동하면 안 되겠죠. 사람스럽게 주행을 해야 하고 사람의 운전 행동에 대해서 분석을 해야 됩니다. 그래서 그걸 바탕으로 판단을 하게 되죠. 이거를 주행 정책이라고 했습니다. 마땅히 매칭되는 말이 없는데 플래닝이라고도 하고, 이것은 이제 판단의 영역이라고 말씀드린 바 있었죠. 저는 이제 공부를 하면서 재밌었던 시간이었는데 여러분 입장에서는 어떠실지 모르겠습니다. 이 뒤에 굉장히 길어요. 그러니까 잠깐 정지를 해두시고 화장실도 한번 다녀오시고 물도 하나 준비하셔서 영화 한 편 보신다고 생각하시고 보셔도 괜찮을 것 같습니다. 함께 보시죠.
Good afternoon, everyone. I'll focus on software in this lecture, and I'll talk about the three major elements to making a fully autonomous car. And the way we look at it, we call them pillars. One is related to sensing. Most people have an intuitive understanding what it means to sense and interpret the sensing information. The other one is mapping. What kind of maps? How do we create these maps? How do we update these maps? And how they are connected to sensing? And the third pillar is driving intelligence. We call this driving policy. And this is the reason that we take driving lessons. It is the ability to understand a multi-agent type of scenario where we need to understand human driving behaviors. We need to know how to merge into traffic. So it goes more than just the control theory. It's the high-level decisions, the planning, and how all of this is connected. Right? The main theme of the talk today is that the sensing, mapping, and the driving policy, they must be handled simultaneously. These are not three separate blocks, sensing done by company A, mapping done by company B, control driving policy done by company C. It has to be done all together because they influence each other. If you do it separately, then you start raising unreasonable demands on each block. Unreasonable demands meaning that it will never work. By looking at it as one big element, then you can kind of play with the demands and make something that would work. Okay, so this is the main theme of the talk today. So let's 2 slides about sensing, because sensing is the most intuitive part. I want to skip it even though that, most of what we are doing at Mobileye is sensing. So in terms of sensing, the purpose of the sensing is to build an environmental model. And environmental models, where are all the moving objects, where are all the vehicles, pedestrians, obstacles, where are all the path delimiters like a curb, guardrails, barriers, where are all the drivable paths and their semantic meaning. All of this, 360 degrees, is an environmental model. So let's just see what goes into it and what is challenging and what is not. So the first one is all these moving and stationary objects. So first, achieve zero false positive, zero false negative. Zero false positive is already part of ADAS, but zero false negative is really what is necessary for autonomous driving. Vehicles at any angle, not just the rear of the vehicle. Pedestrian detection needs to be enhanced considerably because we need to know what the people are doing. Not only that there is a pedestrian there, but is the pedestrian looking at me? What is the pedestrian doing? Where is the pedestrian standing on the sidewalk, on the road? And then general obstacles. The point I want to make here is that this is the easy part. This is a natural growth of driving assist. Okay? I'm not saying easy is maybe not the right word, but it's the natural growth of driving assist. The second element, called this path delimiters, we're talking about detecting the free space where the host car can move, detect any boundary. Boundary could be a curb, a guardrail, a row of parked cars, any boundary, and label the type of boundaries. So I would say that this is kind of the first leap beyond ADAS, but even that is not correct. The Euro NCAP 2018, 2020, they talk about specifications of any boundary, even though they're a bit vague what they mean by any boundary, but clearly it's moving towards being able to infer path delimiters as part of ADAS, part of driving assist. But this is one leap beyond where we are today with driving assist. The third one is really the killer. It is drivable paths. It is understanding where all the drivable paths are, reading all the pavement markings, understanding, connecting the drivable path with traffic signs, associating semantic meaning to each drivable path. Is this path heading to a highway exit? Is the path going straight? Is there a split? Is there a merge? All the stuff that we take for granted when we are driving, these are very, very complicated. And this is not part of driving assist today. Driving assist today detects the left and right lane. That's it. You want to do lane departure warning, lane keeping assist. You don't care about all the rest. This is a very, very big leap beyond driving assist. And this is where most of the challenge exists in going from driving assist today to autonomous driving. Another slide I want to make sure is, why do we need surround camera? So I think conventional wisdom is that you need a front-facing camera. You need to read. There are things that only a camera can do. You need the color of the traffic light. Only a camera can tell you that. You need to read the traffic signs. Only a camera can do that. You need to detect the lanes. Only a camera can do that. So clearly, you need a front-facing camera. But why do you need surround cameras? Because there are many sensory constellations that talk about, say, have a front-facing camera, front-facing radar, four-corner radars, laser scanners in the front and the back, and you have kind of a 360-degree cocoon. I would say that yes, for highly autonomous driving in highway settings, that's fine. Once you get into city traffic, where things are becoming much more complicated, that is not sufficient. And let me try just to show where things are. So why would we need a corner camera? We need a corner camera first to detect pedestrians when we are kind of turning, be able to detect the pedestrians. This can be done with a laser scanner, let's assume. We need to have a precise boundary of the vehicles, not just knowing that there is a vehicle there, but the precise boundaries of the vehicle. So we need more resolution. And the biggest issue is we need to understand the drivable path. Drivable path is texture. Only a camera can give you that information. So therefore, we need a camera in the corner. Why would we need a camera looking kind of a wing camera? Again, we have pedestrians. We have three-dimensional objects. We need to associate a lane assignment to the car that is on the side. So we need to read the lanes. That's texture. And also the path delimiter confirmation. So the front-facing, understand that there is a curb there. We want to confirm that this curb exists and have the side camera see that curb. And then why would we need a rear camera? Again, we have pedestrians and three-dimensional objects, but we want to have redundancy for the front-facing capability of detecting lanes. So this gives you a 360-degree. So this does not mean you don't need radars and you don't need laser scanners, but you must have cameras 360 degrees if you want to enter into city traffic. So that's all what I want to say about sensing. I want to go into next issue is planning, the driving policy. So I took here something from the internet about, that today's experimental cars, in this case it's Google's, but I think all of them are like that, are too conservative. And they create accidents by being non-human-like driving behaviors. And the point I want to make here is that driving is a multi-agent game. We need to understand human driving behavior in order to merge into traffic in a safe manner. So we need to plan. So here I want to kind of make the point of what is the difference between sensing and planning. So sensing is the present. I have an image, I have a video, and I want to know where all the objects are, where all the path delimiters and so forth. I want to sense the present. When I'm sensing an object, a vehicle, I'm treating it not as a human behavior. I'm treating it simply as an obstacle. So it's sensing the present. It's a single agent game. It's only me in the road. And it's perfectly predictable. That means if you give me enough input-output examples, I can put a machine learning algorithm that will learn how to predict, given an image, given sensory information, tell me where all the objects are. What is the technology? Technology is the deep supervised learning. It's part of machine learning. Today it's very, very popular to talk about that, but this is really the tool of sensing the present. What is the driving policy? Driving policy is planning for the future. It's not the present, the future. It's multi-agent game. It's not only me. It's other behaviors, and these are not just obstacles, they are behaviors. I need to understand them. And I need to ask questions, what will happen if I do this? What will happen if I do that? And it's not perfectly predictable. And the technology behind that is called reinforcement learning. So what is that? You want to learn a policy. You have states, you have actions, and then you have rewards. And you move from state to state by taking an action. Action could be change lane, an action could be slow down, an action could be accelerate. And state is the current sensory state that you are in, and you are getting a reward. What makes this going into the future that the instantaneous reward is not what you really want to optimize. What you want to optimize is the accumulated reward, something that goes accumulated into the future. So say, for example, I want to exit in the highway, and I know that the exit is 3 kilometers away. I can start changing lanes, and all of this gives me zero reward. But the reward that I'm really interested in is, do I successfully exit the highway or not? So you're looking at something really accumulated into the future. And the learning process is, you observe a state at time t, you decide on an action, you get a reward, and you move to state number t+1. Okay? In supervised learning, actions do not affect the environment. Therefore, you can collect a lot of training examples and build a optimal policy from state to action. In supervised learning, the effects of the actions is local because we're not accumulating rewards. And given the correct answer, in supervised learning, we're always given the correct answer. We have an input and output, and the output is always correct, and therefore we're training a learning algorithm. In reinforcement learning, because of the reward, we're not always given the correct answer. So it's a more complicated problem. This is it's part of a paper that we wrote, is about our algorithm for doing reinforcement learning using a recurrent neural network. The gray box there is a piece of a network that is then replicated over time. And there is a state going into an action, and there are 3 deep neural networks there that are building the capability. And let me show you some examples here. So this is a toy example just that we get the idea of what does it mean to plan ahead. So the idea here is that the red box here is a car entering into a roundabout, and the roundabout is busy. So you need to squeeze in. And there are 2 types of behaviors in the roundabout. There are the blue cars, which are aggressive. Once they see you try to squeeze in, they'll accelerate, not want to let you In Israel, it's very, very common. That's all the drivers are like this. Okay? And then the green cars are more relaxed. They see you squeeze in, they'll slow down. Now, the point is that the red car, the agent doesn't know about that. All what he tries to do is to squeeze in and creates accidents. And these accidents are the negative rewards that he tries to optimize. And this is how it looks after the agent has learned. So you'll see that you saw the blue box accelerating, and you see that the red one is squeezed in incorrectly. Okay? So this is a rather difficult problem because it's something that's difficult to do in a rule-based type of thing. Let me skip this slide. Okay, now the point is, why are sensing and driving policy really coupled together? Why not have sensing, company A, driving policy, company B, have expert do the sensing, have an expert do the control? Why are they coupled together? They coupled together because what is known as abstraction. So if we want to build a system where receiving sensing information on the left-hand side, in this case I simply wrote video, but it could be additional sensing information. And then we take the big problem of sensing and we break it down into modules. In this case, these are different deep networks. One does object detection, the other one does drivable path delimiters, and so forth and so forth. You break down the problem into components, and then you have another deep network that will do this driving policy. Now, this part of the abstraction, this breakdown is kind of obvious. From an engineering point of view, you have a big problem, you break it down into its component. But what about the driving policy? How do we decompose this into modules? Now, in the area of reinforcement learning, this is called temporal abstraction. So the idea is the following. In an end-to-end system, right, we want to learn a policy, and this is the pie on the left, that takes the sensing state, takes also a state of things that we want to remember from the past, and maps it into control parameters. Say only 2 parameters, accelerate and steer, left or right. Okay? So you have all the information from sensing, and then you map it onto your control. This is not good. It means you are not breaking it down. Breaking it down is called temporal abstraction, is that you are building a policy not directly to the control, but there are all sorts of, you can think of this also as a hierarchy. Are you in a highway? Are you in a rural road? Are you in an urban setting? Do you want to take over? Do you want to follow? So first you want to make this decision. Once you have that decision, you go into another hierarchy of another policy and so forth. So they're breaking down these policies. So you can see now how these two are connected. Because in order to do the right policies, you need to break down the sensing into many, many parts. So you cannot have one company doing the sensing, the other one doing the policy. It has to be done together, either through a very, very strong collaboration or have one company do both of them. Okay? Let's go, as the last 9 minutes that I have here, let's go into mapping. Okay? With mapping, the situation also needs a definition. Right? So with sensing, we know what sensing is. There are cameras, radars, laser scanners. With mapping, we humans do not need a map at all. So why do we need a map? Right? There are navigation maps. These are the existing maps. And then there's the high-definition maps, the TomTom and Here and others are talking about high-definition maps. And then there's the Google three-dimensional cloud of points type of map. So when we talk about mapping, we have to decide what do we mean about mapping. And then there is localization. If there's no map, we don't need to localize ourselves. In a navigation map, a GPS is sufficient. A few meters of accuracy is enough. But when you talk about high-definition maps, you want to use the maps in order to do control. The accuracy has to be centimeters. So when you talk about maps, we have to define what it means, what it means by a high-definition map, and then we have to figure out how to localize, because the GPS would not give us this kind of accuracy. So when we look about what are the requirements to enable autonomous driving, we see first, it has to be, the update has to be a continuous process. Right? I don't care how we build the map. The real issue is how do we update this map. Now, if this map is safety critical, because we're doing autonomous driving using the map as redundancy to path information to drivable path, using the map to get foresight, to know where things are going ahead beyond sensing, this is safety critical. If it's safety critical, it has to be correct all the time. It has to be correct all the time. The update should be done continuously. Okay? So if an update done continuously, it has to be crowdsourced. I don't see any other way of doing continuous update without crowdsourcing. If it's crowdsourced, then the data per vehicle per kilometer should be very, very small. We are talking, what I'll show you, about 10 kilobytes per kilometer, so that we can send it through existing communication infrastructure like 3G, LTE. And finally, because we are in the automotive industry, we want to be very, very low cost, right? So we want to use existing infrastructure. What is the existing infrastructure? Cameras are in every car, or will be in every car, because of the safety regulations, the driving assist. By 2020, 2022, there is no reason that every car would not have a front-facing camera. So this is something that is already there regardless of autonomous driving. Second, communication from car to cloud is also something that is coming regardless of autonomous driving. So let's take these two elements and use them to build the maps without adding any new hardware. So the idea is to build a concept where the 3-dimension is sparse. Sparse meaning that we're looking only for landmarks. We're not representing 3D in a detailed manner. And we're representing the road. The road is a one-dimensional type of information. The lanes are one-dimensional information, and those we are representing them in a dense manner. And therefore, we can put this together in a very, very low bandwidth, this 10 kilobytes per kilometer. So in terms of a landmark, we're talking about visual landmarks. And in the next slide, I have here a list. We're talking about signs, rectangular signs, triangular signs, all sorts of traffic signs, road markings, traffic lights. Here we're talking about more than 20,000 different, a vocabulary of 20,000 different items. And then poles, reflectors, horizontal structures like bridges and tunnels and so forth. Anything that is fixed in the world is a landmark. We use these landmarks to fix the location, the localization drift. So here's an example in somewhere in Germany, just to get a sense of the density of landmarks you can get. Okay, so in this case, these are pavement markings and traffic signs and poles and so forth. And in terms of density of landmarks, if we include lampposts and reflectors, we get, in the worst case, it's about 200 meters, the maximum distance between landmarks. Okay? This is important because you need to have high density in order to fix localization drift. And then what we do, the information from the camera builds an environmental model, builds the lanes, and we call this harvesting. This is on the clip that you see. The camera stitches all this information, uses ego motion in order to put everything in the same local coordinate system, and then uses the landmarks to fix localization drift. Just to get an idea of this ego motion, today ego motion has evolved to becoming something very, very accurate. This is a comparison between the ego motion and a 30,000 euro INS. So it's very, very accurate system, and the ego motion is right there all the way compared to a $30,000 inertial sensor. And then all these packets are sent to the cloud, and then they are integrated into a high-definition map that we call a roadbook. And the roadbook has three usages. One is to localize, because we can use the landmarks to localize. HD map content. It can enrich existing HD maps, or it can replace all the concepts of existing HD maps. And then you can use it to actuate control using map content. So let me show you some examples. So this is a localization. You see the landmarks, and you see the point here in terms of localization. All this map has been built by several drives in this area. This is using it for control. So what you see here, these lanes are not by sensing. This is taking the map and projecting it onto the image space. And it's so good that you think this is sensing, but it is not sensing. Let me show you a bit more. Here is a Nissan Demo that was in San Jose, January this year. It's a complicated city driving, 15 kilometers of urban driving. And what you can see here, the point is the 3 points. These are the control points that the system would provide. And you can see that it runs in areas where sensing would find it very, very difficult, like in a turn. You don't see the lanes in a turn. And this mapping concept, what enabled the demo to work well. This is another demo in March, again in Japan. Here's an idea. Again, the point here is this 3 points, the control points that are outputted by the system, but you can see the complexity of the driving. This is really city traffic driving enabled by these kinds of map concept. This is a proof of concept activity we're doing with Volkswagen, building now maps in complicated areas. This is, for example, in a junction. This is looking at a 28-kilometer route here in Germany. And this is the projection of the map on Google Maps. So this gives you an idea of some idea of accuracy, right? So you see that these colored lines are more or less on top of the Google Maps, right? So we get accuracies of centimeters here. This is the route that is being taken. So this is the using it for control. So you can see that we're using it for control because these two lines here, right? Sensing cannot detect these two lines because of the obstruction from the vehicles. But as we go forward, you'll see that these are exactly on lanes. I think we'll see that more or less here. Yeah, you can see the lane markings, right? So again, this is the projection from the map onto the image space, and you can see how accurate it is. And here again, you can see that you get the foresight that you saw that the lanes here. See how foresight. This is foresight. This is not sensing. So you can clearly see this is a projection from a map, and not sensing. Again, these are complicated areas as part of testing that we're doing. And last 5 seconds. So I was kind of on the spot. So to summarize, the point I was making here, I didn't talk about hardware, I didn't talk about the chips, IQ chips, central computing of the car and so forth. Those are very, very interesting topics to talk about and critical topics to talk about. What I wanted to point the attention is that there's more than sensing going on here. And the other things that are going on here are not easier than sensing, and in some cases are even more complicated than sensing, especially the driving intelligence, the driving policy, and also how do we manage the mapping? Because without managing the mapping, we will not have autonomous driving. Because we need the map for redundancy, we need the map for foresight, and it has to be continuously accurate, therefore it must be crowdsourced, and this has to be handled. And I showed some examples of what we're doing there. Thank you.
재밌게 보셨나요? 어떠세요? 조금 중간에는 어려운 문제들도 제가 넣으면서도 있긴 했는데 개략적으로 이해하시면 되실 것 같아요. 어제 바뀌었던 이 뒤에 배경이 있잖아요. 이게 몬스테라라는 식물이래요. 이게 배윤희님께서 말씀해 주셨습니다. 개인적으로는 이게 초록초록한 느낌이 좋아서 그래서 예전에 제가 쓰던 바탕화면이었는데 제가 사무실에서 일할 때도 그렇고 집에서도 듀얼 모니터를 쓰기 때문에 양쪽에 이거를 띄워놓으면 심리적인 안정감이 들 때가 많았습니다. 그래서 많이 쓰던 배경화면이고 이번에 바꾸게 된 것이죠. 오늘은 이렇게 마치겠습니다. 감사합니다. 올바른이었습니다.